All right, so now let's discuss the notion of global truncation error. Okay, so the question is the following. So how do sort of two solutions two solution curves differ if they start with different initial conditions? And of course, we need to understand this because once you've taken at least one step of a numerical method, then you're going to diverge in a situation where the subsequent application of the numerical method is being applied to the correct initial data. So you need to ask yourself again, it's like what happens to continuous solutions with slightly different initial data. And so this is what we're going to try to first address. So let's say we have x prime is equal to f of tx, and x0 is some value s, right? And dx, which I denote by f sub x, is continuous. And there's a bounded second f of x, f sub x, right? fx of tx is less than or equal to lambda for the interval of time which we care about, and for sort of this sort of column of data, right? So you have a bound on the time, but then the x can be anything you want it to be. Okay, so so you can think of x as being time dependent, but also implicitly dependent on s, which is the initial data. Okay, so the solution depends on the initial value. Okay, and then let me define u of t to be the partial of x ts respect to s. Okay, and so this leads to the idea of what is called the variational equation for u, right? So we have a variational equation that describes the evolution of u. Okay, so so you can check that u prime is equal to fx txu, and u at 0 is 1. Okay, so let's look at an example of this. Okay, so if you have x prime is x squared, and initial value of x at time 0 is s, right? Then f of tx is equal to x squared, which means that f sub x is equal to 2x. Okay, so the variational equation is it's just u prime is equal to 2xu, right? So u prime is just f sub x times u. F of sub x is 2x, and then u is u, so it doesn't get 2xu, and then u at 0 is 1, right? So that's the variational equation associated with this initial value problem. And so you can first figure out what the exact solution to this first equation. Oh, sorry, I don't want to label that. I want to label this equation, right? So find the exact solution to this, and then from that you can find the solution to the variational equation. Okay, so, and of course you can sort of see that you need the solution to the first equation, in order to figure out the solution of the variational equation, because the variational equation depends on x as a function of time, right? So you need to solve for x first. Okay. So the solution to star, right, is that x of t is s over 1 minus st. So the variational equation then looks like u prime of t is 2s 1 minus st inverse times u of t, and then u of 0 equals 1, and you can check that you can solve this, that u is equal to 1 minus st to the minus 2 power. Okay. All right. So there's that. Okay. So let's state a theorem. Okay. So if we have a bound on fx from above, which we sort of assumed, then the solution of the variational equation satisfies an inequality that the norm of u of t is less than or equal to e to the lambda t for t greater than or equal to 0. Okay. All right. So how do we see that? Right. So you know that u prime is equal to sort of fxu, right? So we can divide throughout by u. You get u prime over u is equal to fx, right? Which is equal to lambda minus alpha t. Okay, so this is what is sometimes referred to as a slack variable, right? We're using the fact that f of x is less than or equal to lambda for all time, all right? And that allows me to write f of x as lambda minus some non-negative thing, okay? So in order to achieve equality instead of the inequality, right? So the condition that f of x is less than or equal to lambda is equivalent to this equality so long as alpha of t is greater than or equal to 0, right? So alpha t is greater than or equal to 0. You can think of this as a slack variable. Okay, and the slack variable allows you to rewrite an inequality as an equality subject to some positivity or non-negativity constraint it's like on the slack variable. Okay, so so we have that, and then of course the left-hand side looks like something like the derivative of a logarithm, right? So I can integrate both sides. So log alpha u, log absolute value of u is equal to lambda t minus the integral from 0 to t of alpha tau d tau, right? This is again non-negative, right? So this is equal to lambda tau minus a of t, which is the integral, right? And then we also know that a of t is greater than or equal to 0 because alpha of t is greater than or equal to 0. Okay? All right. So we know that log absolute value u is less than or equal to lambda t. So this implies that the absolute value u is less than or equal to e to the lambda t, since the exponential function is monotonically increasing. Okay, so that gives you the estimate which you need, right? Which says that again, so long as you have control, it's like over f of x. It's that tells you that this u of t can't grow in absolute value faster than e to the lambda t. Okay. All right. I'll deal with that later. Okay, so let's state another theorem. So the initial value problem is solved with initial data. S and then a slight perturbation of S, which I call S plus delta S, or S, let's just call it S plus delta, right? Then the solution curves at a later time differ by at most absolute value of delta times e to the lambda t. Okay, and the proof is quite straightforward. Right, so x t s minus x t s plus delta, right, is equal to partial respect to s of x t s plus s plus some unknown, let's call that theta delta, right, times absolute value of delta, right. And then this thing here is so actually let me call that theta, right? Yeah, so it's basically again just the sensitivity, if you will. It's like in this delta direction, right? This is just absolute value u of t times delta. This is less than equal to the absolute value of delta e to lambda t, right? Which is sort of what we showed. Okay, so it's just an application of the first theorem, if you will. All right. Actually, no, sorry. It's ds. So it's just the it's just sort of like a mean value theorem type of arguments, basically, right? And then this theta is somewhere between 0 and 1. Okay. Yep, sorry. Okay, so let me state one final theorem, which is the one which we really care about, which is the global truncation error. Right, so what basically it's like we're going to do is we're going to assume that the local truncation error is controlled, and then we're going to use that to infer something about the global error you make. All right, so if the local error at t1, t2, and so on do not exceed delta. The reason why I started at t1 is because usually at t0 you assume that the error is 0, right? So that's the reason why I'm starting at t1. Okay, does not exceed this delta in magnitude. Then the global truncation error does not exceed, well, at Tn, does not exceed delta times e to the n lambda h minus 1 e to the lambda h minus 1 is reciprocal. Okay, so let's prove this. Okay, so we have truncation errors delta 1 to delta n, which are the local truncation errors. At T1 to Tn respectively. Okay. So at T2, right, the error, the global error you have, right, is bounded by the truncation error at the first stage times the amplification plus the truncation error at the second stage. All right, and then at T3, right, global error is bounded by, again, delta 1 e to the lambda h plus delta 2, right? So that's the error. Now at the time 2, then it's amplified by e to the lambda h, right? And then you add an error, the local truncation error at the time T3, right? And you sort of keep doing this. You keep taking the error from the global error at the previous stage, you amplify it by e to the lambda h, and you add its like truncation error at the new time. Okay, so anyway, so you can keep doing this, right? And then what you get is that you can sort of see that the way to sort of see it is that the error at the current time is not amplified. The current error at the previous time is amplified by e to the lambda h. The error at the next previous time is amplified by e to the 2 lambda h, and so on, right? So so you get that the global truncation error is bounded from above by sum from k equals 1 to n of delta k in absolute value e to the n minus k lambda h, right? And then we can bound this error term, so that's, and because all of these terms are positive, well, non-negative at least, right? So they can bound this by delta times sum from k equals 1 to n e to the n minus k lambda h. Okay, and then this is just a geometric series. It's like, and then with a amplification factor lambda h, right? So you know what that sum is. So this is equal to delta e to the n lambda h minus 1 divided by e to the lambda h minus 1. All right, and then if you have that, it's easy to convince yourself that this error bound is exactly this, which we have here. Well, actually, that's exactly that, right? Which is what you need. Okay, so, all right. So finally, it's like we can apply it to something. It's like where the local truncation error is big O of h to the p plus 1, which corresponds obviously to a p-order method. So let's see what happens. So the theorem is that if the local error is big O of h to the p plus 1, then the global truncation error is big O of h to the p. Okay, and the proof is that, right, if delta is big O of h to the p plus 1, right, e to the z minus 1 is big O of z. Where n times h is equal to t. Right, then e to the lambda h minus 1 is big O of h. Okay. Right, because, okay, so another way to sort of see this is that this term here, n times lambda times h, that product, right, is just going to be some final time t, it's like times lambda, so that's sort of, you know, incorporated into the constant. It doesn't depend on h basically, because n times h is just the time, right? The only part which depends on h, it's like in this estimate, is this 1 over e to the lambda h like term, right? And so that's big O of h, right? So so you have to yeah. Okay, so actually e to the lambda h minus 1 is big O of h, right? So you have a 1 over h term here multiplied into this, right? And so it decreases the, and you have control over lambda, sorry, over delta, right? So the point is that the global error is less than equal to delta e to the n lambda h minus 1 over e to the lambda h minus 1, right? And this is equal to delta e to the final time t times lambda minus 1, so this is big O of 1, right, plus divided by e to lambda h minus 1. This is big O of h, this is big O of h to the p plus 1, O h to the p plus 1. This term here is big O of h, and then this is big O of 1, right? So that is equal to big O of h to the p, right? Because that term, 1 over that decreases, it's like the power of h by 1, right? So that's basically what it's saying. Anyway, so that's sort of what you would expect, right? That if you have, again, it's like a local truncation error, which is big O of h to the p plus 1, which is to say that the method is p forward or accurate, right? Then the global truncation error is big O of h to the p. And so the global error scales like, you know, h to the p, right? Which is, again, what motivated us to say it's like the method is ordered p. Okay, so let me just stop here.